I'm going to solve this problem using the slope deflection method. So first, I'm going to suppose an initial displacement, an initial virtual displacement of the structure. So for example, we take the point C perpendicular to the bar CT, because this bar is fixed. And we join this point with D. So we called this displacement delta. As the supports in A and B are roller supports, the movement of the structure will be permitted, and at the end it will be like that. And by these displacements we have here C DC from the old bar to the new bar, in this sense. Here C BC, and here C AC. So now I'm going to take relationships between these three C's, and I'm going to take a look to the degrees of freedom of the structure. So first, there is a theta A and theta B, but we are not interested in, because they are not our unknowns. Then we have theta D, which is 0 because it is a fixed support, and theta C is one now we are interested in. So now I'm going to take a relation between these three C's. So first, we can see that BC is delta divided by this distance divided by this distance. Then CAC, we can observe here that this forms a triangle which has here this delta 1, and this delta 1 can be related with the original delta, because I forgot to put here the angle, which is 45 degrees. So we have here the same angle, and cosine of 45 is delta 1 divided by delta. So delta is delta 1 times the cosine of 45. So here we have that CAC is minus, because it's clockwise, delta 1 divided by L, and CBC will be delta 1 in positive divided by L. So I'm going to, all these C's I'm going to left all in function of CBC, a function of this one. So CDC, which is delta divided by L, we can write it like CAC times L divided by the cosine of 45 by this relationship, and CAC, and this is the same as CBC multiplied by L divided by the cosine of 45. because they are the same but with the opposite sign. So we have now that the degrees of freedom of the structure are this theta c and the c bc. So now I'm going to write the fundamental equations of the system. First I'm going to start with the bar AC, which is articulated fixed. So the moment AC will be 0 because in A is articulated, and the moment CA is given by this formula. And we have here the map created by the external load P, which is minus 3PL divided by 16. So now the bar BC, which is articulated fixed 2, so BC will be 0 and MCB will be given by the same equation as before. This in this case is 0 because we have not external loads or thermal loads or acetylene. And finally the bar CD, which is double fixed. So in this case the equation changes and is given by this formula. In this case it is 0,2, and as we said before, theta d is 0. So NDC in the same way as NCD. In this case here theta d, which is 0, plus 2EI divided by L theta C minus this 0, and this is 0,2. So we have here the fundamental equations of the system. And now I'm going to do the equilibrium in the node C. So okay, so the equilibrium in C, in the node C, we do a little picture of the node C, and we take here this is C, the internal moments created around the node. So we know that the external moments minus the internal moments should be 0. So as we have not external moments, we only have these 3 internal moments. So with a minus sign because all the moments are clockwise. And this is equal to 0. So we take the signs. So we have this first equation to solve the system. I'm not going to write all the values of the moments, but we have it from the fundamental equations of the system before. And finally, to get another equation to solve the system, I'm going to get it by using the P dv, the virtual displacement principle. And it says that the summatory of the external work should be exactly the same as the summatory of the internal work. So I'm going to make here another small sketch of moments around node C. I'm going to put here the reaction of these moments in the supports. We have that MCB should be 0 because this is articulated here. So here, sorry. There is a fixed support, so the moment this is moment CD. Moment DC is not known, and here we have the last the last of the articulated units. So AC equals 0, 2. So now I'm going to take the summatory of the internal work. So we have here MCA, and I'm going to multiply it by AC, and we can see from the picture, from the first picture I have done before, that this CAC is in the same sense at this moment, so the sign is a plus. Now minus, because this moment is CB moment is in opposite direction of BC, minus CD times CB minus DC times CD. So these are this is the summatory of the internal work. And finally, the summatory of the external work. We have an external load P, and the displacement, the virtual displacement was like that, with this delta 1 here. So because this distance are L halves and L halves, we will have here delta 1 divided by 2. So the load times the virtual displacement, 2, and by the relations between delta and delta 1 we can finally deduce that this is P cosine of 45 divided by 2. And finally, by taking the external work and internal work equal, and substituting the values calculated before of all these moments, we have the second equation to solve the system.